All right, hi everybody. Sorry I'm going to be absent for the next couple days. I should be back on Monday, so I will see you then. We're going to go ahead and get started with our new unit. It's Chapter 4, Aromatic Compounds, also known as arenes. So we're going to be learning about benzene. Um, Benzene is an interesting molecule because it is highly stable, but it acts very much like a arene in that it has those multiple double bonds, but it does not act like arene in that it does not undergo addition. It mainly only reacts by substitution. So it does not decolorize bromine. It is not oxidized by normal routes like by potassium permanganate. So no typical addition reactions and mainly reacts by substitution only. So if we were going to say it mainly reacts by substitution only. And so we get into wondering, well, why is it behaving this way? Why doesn't it, if it has this format of C6H6 and it's highly unsaturated, meaning it has alternating single and double bonds, why doesn't it undergo typical addition reactions? It's got plenty of double bonds to be able to do it. And the answer is that it is not simply one alternating single and double bond structure. There is something else going on here. So we're going to take a look at that next. And so let's go ahead and take a look at something called a Kikule structure. It's named after a guy named Friedrich August Kikule. And he is, of course, the guy who did a lot of the investigation into what is going on with benzene. And he proposed the structure of this benzene molecule. Okay, so let's see if I can find a place to draw this out for you. So if I were going to show you what Kikule was representing, he basically said, okay, here is a benzene molecule here, and it is surrounded, of course, by hydrogens on all sides like this. And this is going to be ugly because I'm drawing this with my finger, so I apologize now. And he basically said, okay, so this structure actually exists as these two structures simultaneously. And that is supposed to be a hexane. As you can see, it's terribly ugly and awful, but we're going to do our best there. And basically what he said was that these two structures just change their positions on where the double bonds are. And so I apologize if I drew them in exactly the same spots. No, I managed to move them around. Yay me. 1, 2, 3, 4, 5. And let me erase that because that's just terrible. Let's try that one more time. So we have 2 benzene molecules. And he said that what these benzene molecules look like are a 6-sided carbon chain. Let me see if I can get that out. And I'm going to change my double bonds to here, here, and here. So if you'll notice, all he said basically is that the double bonds are switching places so fast that the typical alkene reactions could not occur. So that's what he thought was going on. And while that is in essence what we really meant with a hybrid resonance structure, we understand it a little differently now. So that's what Kikule kind of represented it as. But nowadays, we have something slightly different going on. And I'm going to try again to draw this. So let's see if I can manage that. And so inside some brackets, we would have the benzene molecule with its double bond here, here, and here, switching places like this. Oh boy, that was a mess. Let's try that again. Much better. And we would switch its places to here, here, and here. And so what's really happening is, and I'm going to change colors so you can see me noting what colors we have, is that this double bond switches over here, and this one switches here, and this one switches here. And then this one is switching back to here, and then here, and then here. And so what they're really, they talk about this being different and that us understanding the difference between these. For me, just as long as you recognize that this is a resonance hybrid, to come to this, and we're going to talk about evidence for this resonance hybrid as we go along. So the idea basically being is that we have a resonance hybrid. What we do not have alternating single and double bonds at any given time. Instead, what we have are completely new bonds that is a hybrid between a single and a double bond. So longer than a double bond, shorter than a single bond, stronger than a single bond, but also not as strong as a double bond. So you can imagine all of that. Let's get rid of that, and let's go ahead and go forward. So the orbital model and what exactly we're going to be drawing here. So this even gets better, and you're going to have to live with me on this as we draw this out. And I'm going to get it all drawn, and then I'm going to talk about it so that we can go, oh, okay, that's what she means. Okay, so first thing we're going to take a look at is the end-on-end formation of the sigma bond. So if you think of this as the two carbons are bonding to each other as these sigma bonds right here, 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 and here. So we end up with 6 sigma bonds. But we also have to pay attention to what else is happening here. So we also need to recognize that, remember, there's not just single bonds to make these sigma bonds. We're also making the rest of the double bond, and that takes in the dumbbell shape of the pi bond. And so I'm going to try to draw this. And as you can see, this already makes a complete mess. There we go. All right. So there we go. And let me just go back a bit because I want to get rid of those. I'm going to redraw that so we can see the pi bonds. So first thing we have as part of the double bond is just the sigma bonds being formed, and that's the end-on-end or axial overlap of these carbon to hydrogen to other carbons, sp2 hybridized orbitals. Now, we attached the 6 hydrogen atoms around it, and we formed 6 C to H sigma bonds as well. So we did that part as well. So, but we're going to build some more because, as you know, this benzene molecule is not only made of single bonds. It's got these hybridized double bonds as well in this resonating structure. So let's take a look and roll on down here. And next we're going to add p orbitals in each carbon, which are going to be perpendicular to the plane of the sp2 orbitals, and they're going to overlap side by side. So the trick for me is going to be drawing this thing so that you can see what this looks like as well. So let's take a look at it. Give me a chance to draw it, and we'll come back. Okay, so as you can see, here we go. There are our sigma bonds, and now we're going to add in the 6 p orbitals and try to show how they all overlap. So you can see where all the sigma bonds really are right now, and I'm actually going to go ahead and get rid of all those sigma bonds. You know they're still there, but we're going to try to think about this 3-dimensionally now, and I'm going to go ahead and draw in, to the best of my ability, these pi bonds, which are existing above and below the plane of the sp2 hybridized. And I told you that it was going to get messy really quick. And I need one more right here. There we go. Okay, now what's so important about all of this is, and I'm going to erase a few of these sigma bonds because those sigma bonds are just, we know they're there. Let's just get rid of them because they make it hard for us to see. And we can see all those sigma bonds inside there, but I want you to also be able to see where the pi bonds are. And those pi bonds are actually occurring in the side-to-side overlap. And I erased something I didn't mean to erase. There we go. They're occurring in the side-to-side overlap of these two p orbitals. So this is where your pi bond is. And this is where this pi bond is, pi bond. And then this is where this pi bond is. And then over here, and this just gets hugely hard to see after some time. So it does have the, basically, if I were to draw two of them and this is where the carbons are, the pi bond overlap happens right in between them, above and below the plane of the sp2 orbital. It is above and below, and we need to make sure that we understand the planar ring has a bond angle of 120 between each of the carbons, and the electron cloud is above and below the ring. And I know I made a giant mess of it, but that's what we need to be able to understand. And when we are making reactions happen with benzene, those reactions are going to happen by breaking the pi bond, not by breaking the sigma bond. And I know we've talked about how the pi bond is not as is easier to break, than the sigma bond is. Okay, so we have two really acceptable symbols to represent benzene. One of them represents the way that Kikule wrote it, which is he drew it like this, and it is accepted today as the representation of benzene. But we understand now that we don't just have alternating single and double bonds, as this structure implies. Instead, what we actually have is a delocalized pi cloud. Remember those delocalized electrons which can move around all the time. And so instead, what we usually do is draw this thing so that it implies that the electrons are delocalized all the time. So it is certainly fine for you to draw your benzene molecule like this. You're going to see me oftentimes draw it as the Kikule structure, because sometimes I need to be able to show the breaking of the pi bond, as you're going to see me do momentarily when we talk about types of reactions. Okay, so a lot of times we have to have the talk about what is IB going to expect that we know. And let's go ahead and put big fat stars next to this. These are reasons, or evidence of the structure of benzene, for the structure of benzene. Okay, and you're going to have to be able to come back with these whenever asked for it. So benzene is not alternating single and double bonds like Kikule said. Instead, it is a resonance hybrid, and there is only one type of carbon-to-carbon bond. It is a resonance hybrid. It is not a single bond. It is not a double bond. It is not alternating single and double bonds. It is one special type of bond. We know this because all bond distances are identical with a length of 1.39 angstroms, and the delocalized pi cloud with electrons distributed evenly around the ring is what helps us demonstrate or explain benzene's inertness. It's really hard to grab an electron out when they're moving all the time and delocalized. We know that either symbol is acceptable, but we need to make sure that we understand the evidence for benzene having this resonance hybrid made of delocalized electrons in the pi cloud. Okay, so we're going to get into now talking about what some common names are, of course, and we're going to go ahead and draw out these structures so that you can see what they are. You'll see IB refer to these common names, but you are not going to see them make you have to know these, but you're going to probably get to know some of them. So, of course, we have some benzene, which we draw like this. And then we have some toluene, which toluene is written as this. And it has a CH3 attached to it. That's a 3, everybody. And then we have some styrene, which has a CH to CH double bond on it. So we have a benzene like this. And then we have a CH double bond to a CH2, just like that. That's called styrene. And then we have phenol, which has a And boy, am I about to draw that wrong. 1, 2, I made it, okay? And phenol has an OH attached to it, just like that. Okay, and then we have aniline. Oh, I forgot my double bonds. Whoops, 1, 2, 3. There we go. And then we have aniline. Come on, draw it right. I get talking too much, and then I'm not thinking. So then we have some aniline with an NH2 attached to it, just like that. And those are the ones that you're going to need to make sure that you probably become quite familiar with. It is not going to be a test question, what does phenol look like? But you will need to be able to recognize what's being talked about here, and it helps to be able to know the lingo. Okay, here we go. So sometimes we have to be able to name certain derivatives of benzene. In other words, when we start to make benzene, for instance, we are going to have one thing attached to it. So how do we call it if it's not got those special names that you heard of? So let's go ahead and see if we can name a few so you can see what they look like. So if it's got a BR on it or a CL on it, you're just going to call it something simple like bromobenzene or chlorobenzene or what have you. So there's that. If it has a nitrogen oxide group attached to it, we're going to call it nitrobenzene. So I'm going to do this because that's so much easier. That would be called nitrobenzene. Let's see if I can write that, nitrobenzene. All right, and we get into things like ethylbenzene or propylbenzene. It's just going to be able to be identified by the group that is attached to the benzene. So that's when it is mono-substituted instead of so in essence, one thing is attached to it. Okay, so what if we have two substituents on a ring? Okay, so let's take a look at, we have a format we're going to follow here. So here is my benzene ring. And let's just say that this is going to count as carbon number 1. And if this counts as carbon number 1, then we might have two substituents in two different places. So carbon number 2 or carbon number 6. So in a 1 to 6 format or a 2 to 1 format would make us an ortho designation. And I'm going to show you what that looks like. You'll get a good idea of what it means then. We might also have a substituents attached on the 3 and the 5 location. That's going to give us the meta location. So they're going to look like they're separated by 3 and 5, or we might end up with a para designation where they're separated by the 1 and the 4. So this gets a little bit easier when you pay attention to what this looks like, and then you're going to get a good idea of how we name this. Now, sometimes we name it with the word ortho as the beginning of the name, and sometimes we simply name it by the letter O or the letter M or the letter P. So we're going to try this out on our first one here, and this one is going to be, there's our benzene, and we're going to have a chlorine here, and we're going to have a chlorine here. So the first chlorine is going to be chlorine number 1. That's going to be number 1. And this is going to be chlorine number 2. So this is going to be in the format of ortho, meaning it's 1 to 2 or 1 to 6. And so we would call this ortho dash dichlorobenzene. Okay, now let's try another one. What if we have those two chloros in a different position? So let me draw another benzene. There you go. And this time our chloro is here and it's here. Okay, so now instead of being in the 1 and 2 location or the 1 and 6 location, now we're in the 1 and 3 locations. So in the 1 and 3 locations, those are going to be in the M or meta. So instead of using the word meta or ortho, I could use the letter M, and now I get to call it dichlorobenzene. And I've run out of space as usual, benzene here. So it's just going to be dependent upon where they are located. So the next one, well, what about if this was para? If this was para, then I would have my 2 chlorines, and I'm going to erase so we can see here. I'm going to erase this one right here. So this is para. For it to be para, it has to be in the 1 and 4 location. So if this was para, and I'm going to draw, there we go, then I'm talking about drawing my benzene with the chloro in the 1 and directly opposite in the 4 location. And so if you number them 1, 2, 3, and 4, so we would call this P dichlorobenzene. That's P dichlorobenzene. And all it really is, the P, the M, the O, really is just showing you the relative locations of the things on there. And you might be going, well, why don't they just use numbers? Because somebody made up this designation, and they could have done 1,4 dash dichlorobenzene, which would have meant the exact same thing. Yes, I know. But they also sometimes use these designations, and you need to know what these designations mean and what they're represented as in their names. Okay. So what if we have more than 2 substituents? Well, things go back to the numbering format. So let me draw a couple of the more than 2 substituents, and we'll see if we can name them. Okay, so let's give these a try here. Here are some good examples here. And a lot of times you have to look for, is there a commonly named one? And so what we need to be able to do is look for, well, is there a commonly named one? It could be. So on the first one, next to example number 1 there, I noticed that it has a CH3 on it, and that is toluene attached to the benzene. So what we named this is by where the chlorines are located. So if the toluene or the methyl group attached to the benzene is considered to be carbon number 1, then I have a chlorine at carbon number 1, 2. Here's carbon number 1. So 1, 1, 2, 3. So I have a chlorine at carbon number 3 for 5 and carbon number 5. So I would call this 3, 5 dash dichloro, and toluene would be how I name this one. Okay. And then I would go to one like this one here. This next one here, this part here makes a phenol. So that means I have a chlorine at carbon number 2 and carbon number 4. So I have 2 dash, comma, 4 dash dichloro. And then we name it phenol for the rest of the structure that it's attached to. Now, here's an interesting one right over the top of example number 2 here. I can see that I have the toluene group right here. Yep, I can see the toluene group right here. There it is. But I see 3 things attached to it. And I see the nitro groups are in carbon number 1, carbon number 4, and that's carbon number 2, 4, and 6. So this is actually called 2, 4, 6, and then it gets called trinitro toluene. And this is much more commonly known by its letters that represent it. It's called TNT. You might know that TNT is also known as dynamite. So trinitrotoluene, there is another one of your ceiling tiles up above that are representative of this. So that is 2,4,6 trinitrotoluene. Okay, let's see. I think we have gotten to the end All right, I think I'm going to stop us right there for today. We'll get into resonance energy tomorrow, but you may move on for today and do the practice of naming assignment that I've given you for today. Thanks, everybody. Bye-bye.